Okay, we've been talking about chapter 9 and stoichiometry, and more specifically, last time we talked about limiting reagent type of problems. Remember that a limiting reagent problem is an idea that when you do a reaction, one of the reactants will get used up first. And that's really important because as soon as that reactant gets used up, there's really no way that you can make any more product. So it's always the limiting reagent determines how much product that you make. One way that you know that it is sort of a limiting reagent problem is a lot of times they will not tell you in the problem it is, but when you look at the reactants and the information given to you, if you have the ability to basically get to moles of each of the reactants, then you know it's really a stoichiometry problem and a limiting reagent type problem. And that's really the key there is, can I get the moles of each reactant? Then definitely stoichiometry happening here. So in this particular case, we talked about a couple of ways that you can do a limiting reagent problem. So for example, we follow our normal steps, balance the equation, convert to moles. And right around here, we could do a limiting reagent calculation. And you do need to do a calculation as we talked about. You could choose either reactant. And basically what you're going to do is just a basic little calculation between the two reactants to basically figure out, if you want to use up one of the reactants, how much of the other one you need to put in there. So for example, here, if I wanted to use up all of my A, how much B would I need in this example up here? Once you figure out how much B that you would need based on that stoichiometry problem, you would look at how much you're starting with. And if you do have enough of B, then that's the excess reagent. If you do not have enough of B, then it is the limiting reagent. At that point, once you determine the limiting reagent, you're just going to continue on with the calculations using the limiting reagent to do your mole to mole relationship to your product, and then your moles to some other unit. The alternative version of doing these problems, as we talked about, is you really could just do two separate calculations. One where you'd go from A and do some stoichiometry and figure out, for example, if we were interested in C, how many grams of C you would produce. Just do a basic stoichiometry problem from A to C. And then you could do a separate calculation from B to C. And whichever one is the smallest number of grams is both your limiting reagent and your theoretical yield. So that's sort of the other approach. It's just basically just do two separate calculations, one from each reactant to the product, and whichever one's the smallest number of grams produced will be both your theoretical yield and your limiting reagent. Speaking of yields, we talked about percent yield, which is our actual divided by our theoretical times 100%. The actual in book problems is typically given to you in the problem. The theoretical is usually calculated from you. So it could be just a basic stoichiometry problem, could be a limiting reagent problem, but you basically will calculate the theoretical in most cases. You divide the two, you get a percent yield. And ideally here, we're looking for a high percent yield, but not super high, because as we talked about, if you go over, for example, 100% yield, then you probably did something wrong. So we want kind of a high percent yield, but not over 100% yield when you're done. Any questions on any of that stuff there? So we did a number of examples last time. I think we just got one more to go to wrap up this chapter. So let's do that one now and see what you come up with. What is the percent yield here? If we start with 100 grams of ammonia and 100 grams of carbon dioxide, nitrogen is 1401. Carbon is 12.01. Hydrogen is 1.008. Oxygen is 16. All right, so take a few moments. Okay, let's take a look and see. We're obviously looking for our percent yield, which is once again our actual divided by our theoretical times 100%. We do have the actual given to us, as it gave it there in our problem, of 120 grams. We need to find our theoretical, which is going to come from our stoichiometry in the equation. Once again, if you're not sure, this two pieces of information here given to you, should tell you that this is a limiting reagent problem because we have the grams of each reactant, which means we definitely could get to the moles of each reactant. So because of that, we know that this is a limiting reagent problem. We need to do that calculation. And as we talked about, it is a calculation. So you can't just look at it and go, I think this one's smaller. So you have to do some type of calculation to determine that. Regardless of what method you choose, you're going to balance the equation, which it is. You're going to convert to moles. So we'll start with that. So moles of our NH3. We'll take the 100 grams. We'll use the molar mass from the periodic table, which gives us 1703 grams per mole. And that's going to give us here 100 divided by 1703. 5872, we'll call it. We'll do the same calculation or similar calculation for CO2, except obviously we will use the molar mass of CO2 from the periodic table, which is 4401 grams per mole. That's going to give us 2.272 moles of CO2. Remember, you can think of these again as your starting amounts of each of these guys. Because it is a limiting reagent problem, I'm going to do that calculation between our two reactants. So in this case, I want to find out how much CO2 is needed to use up all the NH3. So I'm going to take my NH3 moles that I'm starting with. I'm going to go to the equation and look at the relationship between NH3 and CO2. And from the equation, it's a 2-to-1 relationship, which means 2 moles of NH3 on the bottom, 1 mole of CO2 up on top. And again, that's just the coefficients. And that's going to give me 5.872 divided by 2, 2.936 moles of CO2 is needed. This is where I'm going to compare how much I need to how much I'm starting with. And I hope we could clearly see I do not have enough in this case. I have 2.2 to start with, but I actually need 2.9. So because of that, that means that the CO2 is the limiting reagent. The NH3 here would be our excess reagent. Any questions on that? Now that I've determined which one is my limiting reagent, remember it is the one that determines how much product I'm going to make. I want to make sure I'm using the starting amount of the CO2 in this case. So I'm going to go to step number 3 here and go 2.272 moles of CO2. I can now do the relationship between CO2 and my product, which is a 1-to-1 relationship between those two. So 1 mole of CO2, 1 mole of our product here, going to give me 2.272 moles of our product. This would be technically the theoretical yield in moles. But since my actual yield is in grams, I do want to convert these moles into grams. So I will need the molar mass of that product. That is 2 times 1401 plus 4 times 1.008 plus 12.01 and a 16. That's a 6006. I feel like we've seen that number earlier. 6006 grams per mole. Moles are going to cancel. And this will give us about 136.5. And this number here would be our theoretical yield in this case. Any questions on that there? Now that I have my theoretical yield, which is the bottom part that I need for the percent yield, all that's left to do is divide. So we're going to take the 120 grams divided by the 136.5 grams, times it by 100%. And that is going to get us here about 87.91. Not too bad. Percent yield, yeah. Any questions on any of those steps? Again, the alternative method for you to do would be Start with the grams of NH3 and figure out how many grams of the product it would produce. Do a separate calculation starting with the grams of CO2, figure out how many how many grams it would produce of the product there. And again, whichever one's the smaller number, which in this case would be the 136.5 number, would be your theoretical yield. Question on limiting reagents, stoichiometry, excess, limiting. All right, that wraps up chapter 9 here. So we're going to go off to chapter 13, I think. All right, we are off to chapter 13 here, talking about gases. That obviously is the state of matter where everybody is flying around from each other. They have a lot of energy, obviously, as they are flying around. And one thing that we associate with gases is pressure. And the pressure comes from collisions that occur. So as they're flying around, they're banging into like the wall. It's like knocking on that side. I feel like they knock a lot on our side. And it's gonna probably come. And it causes a lot of pressure as they're colliding with the container and other gas molecules floating around. Now, when we talk about gases, substances that exist as gases under normal conditions, let's talk a little bit about what normal conditions are. When we talk about normal conditions, we're talking about a pressure of 1 atmosphere, and that's what the ATM stands for here, which is a unit of pressure, and 25 degrees Celsius. And that's sort of like normal, sort of everyday temperature pressure combinations. And under kind of normal conditions, when we think of ionic compounds, which are metals and nonmetals, are cations and are anions, they typically do not exist as gases under normal conditions. In fact, you could probably heat the heck out of an ionic compound, and because it's held together by a really strong intramolecular force, which is that electrostatic attraction, it's going to stay together pretty much. And it actually would just start to melt before it would actually go into the gas phase. So for example, if you think about early on when you did some of those experiments where you took the evaporating dish at the end of the experiment and you evaporated off all the water, bless you, and you're left with a solid that was left over in the evaporating dish, that solid's an ionic compound, and you could have kept heating that thing. It will never kind of evaporate away because of that really strong attractive forces. Now, molecular compounds, which are really covalently bonded together through sharing of electrons, are a little bit different. There are certain things that are gases under normal conditions, like carbon monoxide, carbon dioxide, hydrogen chloride, ammonia, and methane, which are just gases under normal condition. But a lot of molecular compounds are solids or liquids at room temperature. But one of the main differences between a molecular compound and an ionic compound is it is much, much easier to turn a molecular compound into a gas than an ionic compound. So if we take just for example, water, which is a very good example of that. When we look at just one water molecule by itself, the covalent bonding that's happening between the oxygen and the hydrogen on one side and the oxygen and hydrogen on the other side, that is what is known as an intramolecular force. And that's the force that basically holds together one molecule without it falling apart, which in this case is basically the covalent bonding, the sharing of electrons. When we get a couple water molecules or more together, water is polar, as we know. And it has a positive side and a negative side where hydrogen is more positive, oxygen is more negative, and that is how different water molecules basically interact with each other. This is what is known as hydrogen bonding in this particular case, and that is what is known as an intermolecular force, and that is the force that holds together one entire molecule, like this water molecule, together with another water molecule. Now, the strength of that force determines at what point it will go into the gas phase, but any intermolecular force is always much weaker than an intramolecular force. And water is also a really good example of this. We know when we go heat up water to make some pasta, for example, when we start to heat it up, the bond that breaks first is actually the bond between the different water molecules. And that allows this water molecule to go off into the gas phase, this one to go off into the gas phase. If it was different and the intramolecular forces were weaker, when you would go heat something like water, you would be breaking this bond and this bond, which means as you're trying to make pasta, you just made some oxygen gas and hydrogen gas, which is probably not a great thing if you have fire underneath there as you're cooking it as well. You'll never get to the pasta part probably. And we know that doesn't happen. So when we have an intramolecular force, that is always much weaker than any intramolecular force, and that's the one that's going to break. Now, when we think about something like methane or any type of organic compound, like propane, butane, those guys are gases under normal conditions. And that's because guys like these are nonpolar, and nonpolar molecules are basically held together by what's referred to as dispersion forces. And dispersion forces are like the weakest type of force that you could have. You look at it wrong and it's just going to kind of break apart from each other. It's not going to be held together very, very strongly. And that's why when we think of things like methane, propane, butane, they are gases under normal conditions. That's also why when you get to organic chemistry, if you're going in that route and you go to lab, they typically will throw you into a fume hood, not you, your whole body, but you will work in a fume hood. And that is because a lot of organic chemicals that you use are very volatile because they are held together by these very weak forces. And volatile means it could go into the gas phase super easily. So even though it's in the liquid phase, you open the cap and it's going to go into the gas phase really, really quickly. And a lot of them are very flammable, which is why they kind of put them in fume hoods to, set the place on fire as well. So because of these intermolecular forces, if it's a really strong intermolecular force, there's going to be a lesser chance that you'll find it as sort of a gas under normal conditions. But if it's something that's held together by a really weak intermolecular force, it's very commonly going to be found sort of as a gas. Any questions on that there? Now, let's talk about some substances that obviously are gases under normal conditions. Our hydrogen, nitrogen, oxygen, fluorine, and chlorine. So these are our diatomic molecules, which are elements. They're all gases. Ozone, which is a gas, which is O3. And then obviously group 8 on the periodic table. Our noble gases are helium, neon, argon, krypton, xenon. All the ons are noble gases. They are monoatomic, which means that they do come as ones, as opposed to hydrogen, nitrogen, oxygen, fluorine. So on the periodic table, pretty much to the right-hand side there, and our hydrogen, under normal conditions, we're going to find these guys as gases. Now, when we talk about gases, there is a difference between the word gas and the word vapor. And when we refer to something that is a gas, that means under normal conditions, we would expect it to be in the gas state. And a vapor, though, on the other hand, is something that under normal conditions is actually not in the gas state, but it's in a solid or liquid state, but can easily be converted into a gas. And water, again, is a very good example of that. That's why oftentimes when we have water in the gas phase, we call it water vapor, because water gas just sounds funny. But we call it water vapor because water is normally found in the liquid state, but can be easily converted into a gas. That's why we also call methane gas, because it is normally found in the gas state under normal conditions. Any questions on that there? All right, so one of the most common sort of properties of gases that we deal with, as I mentioned, is pressure. And the pressure of a gas is one of the things that we do measure. It is a result really of how many collisions that gas molecule basically has. So there's a direct relationship between the number of collisions and the pressure of that sort of situation. Obviously, the more collisions you have, the higher the pressure you will have. The less collisions that you have of a gas molecule, the lower the pressure there will be. So let's talk about how we measure pressure. And one of the common ways that we measure pressure is with a barometer. And a barometer is, well, a classic barometer. We don't have classic barometers anymore in education. They took them all out because they're usually made out of mercury. But a traditional barometer is like a mercury kind of pool of mercury. a sort of glass tube in the mercury. And as the atmospheric pressure pushes down on the mercury in the tube will start to rise. And mercury is an unusual substance. It actually has a reverse meniscus. It actually goes upwards rather than downwards. And that is because the attractive forces between mercury and itself is actually stronger than the attractive forces between mercury and the glass. And that's unusual because normally we see a meniscus going in this direction. You would actually, if it was mercury, read from the top of the meniscus in this particular case. Now, a barometer was invented by a guy named Torricelli, and we have very common units that we typically will see with pressure. And I would say that these are probably your big three units in terms of pressure for your chemistry career. ATM, which is an atmosphere. 1 torr, which I'm assuming is named after the guy who invented the barometer there, is equal to 1 mmHg. That is millimeters of mercury. And that is because on a traditional barometer on the glass tube is frankly a ruler. And you would use the ruler to measure where the mercury is. Very commonly, you would measure in inches, sometimes in centimeters, and sometimes in millimeters. And that's why it's called millimeters of mercury, because that's basically how you would take a reading, basically like a ruler on that. Now, 1 torr and a millimeter of mercury are equal to each other. It's a 1-to-1 relationship, which means if you need to convert between those two, pretty much just change the units. It's going to be the same number. But the relationship between an atmosphere is equal to 760 millimeters of mercury and 760 torr. That means 760 is an important number. If you have atmospheres and you want millimeters of mercury, or torr, which is kind of the same thing, you're going to multiply by the 760, and that will get you your millimeters of mercury or your torr. If you're starting with millimeters of mercury or torr and you want atmospheres, you're going to divide by the 760, and that will get you to atmospheres. You definitely need to know these numbers for sure. Yeah. And they do come up a lot, including the 760 as a way to convert between those two. As I mentioned before, probably the big three in terms of units that you'll use in probably your entire chemistry sort of career, but there are other units associated with pressure that does pop up occasionally. So let's talk a little bit about some of those other units. Here's a much prettier picture of a barometer. And again, you can see the meniscus is going in the opposite direction here. And once again, on this tube would be like a ruler where you would take a measurement. Some other common units of pressure are pascals and kilopascals. Physics, I think, uses that a lot. So 1 atmosphere, 101,000 pascals, and 101.3 kilopascals. PSI, pounds per square inch, right? 14.7 equals 1 atmosphere. And hitting the bar there is equal to 1 atmosphere. 1.01 bar is equal to 1 atmosphere in this case. So I would say you should be familiar with these, but really the previous page is probably the three that's going to show up 99% of the time in chemistry, at least, in most problems. Any questions on that there? Okay. So let's talk a little about some of our gas laws here. And the first one we're going to look at is Boyle's law. And when we talk about gas laws, there's 3 variables that we oftentimes come across, which is pressure, volume, and temperature. And in a lot of cases, we may only be looking at 2 of these variables and keeping the other one constant. And that's what Boyle did. Boyle's law looked at the relationship between pressure and volume, and it kept temperature constant. So what Boyle basically found was that if you took a volume of gas, and it was a really small volume of gas, like my little box there, and I have my gas molecules in there. Clearly, those gas molecules do not have a lot of room to fly around in, right? So they're not going to fly around too far before they start colliding with things and have a lot of collisions. So what he found was that if you have a small volume, because there's going to be an increase in the number of collisions, you will actually see an increase in the pressure. So sort of an opposite relationship. As the volume goes down, the pressure will go up because frankly, everybody's on top of each other and everybody's going to start colliding. Now, the opposite he found is true as well. If you have a little larger of a volume and you put your gas molecules in there, it's now going to take a little bit longer for everybody to have collisions because there's a little bit more room for everybody to fly around in. And when we see the volume increase, we actually will see the pressure start to decrease in this case. So again, sort of that opposite relationship. Another thing that Boyle found was that if you took a gas and you kept the temperature constant and you did a bunch of different sort of pressure volume measurements, so pressure and volume measurements that go together, no matter what measurements you look at in that situation, if you take the pressure times the volume, it will always hit a constant value. So if you take a bunch of pressure and volume measurements for the same gas under constant temperature, and you multiply the pressure and volume numbers that go together, you'll always hit a constant value. And that's kind of important because now we could kind of set PV equal to a couple of conditions, and we could get really what we call Boyle's law here, which is our P1 times V1 equals P2 times V2. This is Boyle's law. This again is at constant temperature. In this particular case, the pressure units does not matter as long as they are the same units on both sides. And the same thing with the volume. The volume units here do not matter as long as they are the same on both sides, so everything cancels out correctly. So this is kind of like a before and after situation. You change something like the volume or pressure, and you can see how the other variable is affected by that. So P1 V1 equals P2 V2. Clearly, you need to know that as well. And that is Boyle's law. And this is a graph of Boyle's law relationship. We see at a much smaller volume, much higher pressure. We give everybody a lot more room to move around it. A much larger volume, a much smaller pressure occurring there. Again, because the number of collisions are going to start to decrease in this case. All right, so let's try one here. We got a balloon, has a volume of 0.55 liters at sea level. 1 atmosphere goes to 6.5 kilometers. The pressure is 0.4 atmosphere. What will be the final volume of the balloon? So take a moment or two there and see what you come up with. We don't have a lot of gas laws to choose from. That will not be the case shortly. So a lot of times when you're doing gas problems, a really good way to approach it is just to pull out the information and label, what they are. Are they a volume? Are they a pressure? Are they a temperature? So if we do that here, we have a volume that is 0.55 liters. We have 1 atmosphere, which is a pressure. We have 6.5 kilometers, which is useless in this problem. We have another pressure that is 0.4 atmospheres. And we are looking for a volume. So you should be able to kind of really see Boyle's law there just from sort of labeling what everything is. A lot of times that could kind of point you in the right way in terms of the formula that you should use. We're going to call the first one's 1 and the second one's 2. It really doesn't matter as long as you keep everybody together that goes together. And we want to check units. So atmospheres and atmospheres. So we're good to go on that. So we'll go P1 V1 equals P2 V2. In this case, we're solving for V2. Although it's not written as a fraction, you could think of those guys as being on top, and all these gas laws, if you want to quickly rearrange something, you just move something to the opposite location, which means it's going to go on the bottom there. And that will be P1 V1 P2 is equal to V2. So whenever you go across the equal sign, that guy ends up in the opposite location of where it's at. And that means all we have to do now is put in our numbers. We got 1 atmosphere, 0.55 liters divided by 0.4 atmospheres. Atmospheres cancel, going to give us units of liters, and we're going to hit a 1.4 liters in this case. Any questions on that there? Now, understanding the relationship of Boyle's law, we could really kind of double check in a sense that we didn't screw something up. It is very common that people sometimes will reverse numbers or inverse numbers. We see that the pressure here went from 1 atmosphere to 0.4, which means the pressure goes down. That means my volume should go up, right? Opposite. And we started at 0.55 liters. We ended at 1.4. So it is going in the correct direction. And that's a good way you can kind of check yourself sometimes. Just to make sure maybe you didn't flop a number around and stuff like that. Obviously here, if you got less than what you started with in terms of the volume, you're not really going in the correct direction in terms of the relationship. Any questions on that there? All right, the next gas laws we're going to talk about is Charles' law and Gay-Lussac's law. And they dealt with a couple of relationships. Charles dealt with volume and temperature. Gay-Lussac's dealt with pressure and temperature going on here. Let's talk about what's happening in each of these situations. In Gay-Lussac's law here, he dealt with pressure and temperature and kept volume constant. So we had a constant volume here, but pressure and temperature changed. That means that when I look in this situation and I have my gas molecules here, if I were to increase the temperature of this, would my gas molecules be moving slower or faster? They're going to be moving faster, right? If you light a fire under somebody, they move faster, hopefully. That means that these guys are going to be moving around really fast, and that's going to cause a lot more collisions to occur. And what we will actually see is a increase in the pressure in this case. Now, the opposite is kind of true here. If we take our same sort of gas molecules and I lower the temperature, if I lower the temperature, that means that our gas molecules are going to be moving slower. Dramatic drawing of slower. They're going to be moving really, really, really slow if I really kill that temperature. And that's going to cause a lot less collisions to occur. And that's going to see our pressure start to decrease. So in a Gay-Lussac situation where we're keeping the volume constant and the temperature goes up, so will the pressure because we'll have more collisions. And as the temperature goes down, so will the pressure because we'll have less collisions. Now, if we look at Charles' law really dealt with volume and temperature and actually kept pressure constant. So in this situation, what's going to happen is this. If I take a container that has some gas molecules in there and I increase the temperature, as we saw on the right-hand side there, if the volume stays put and does not move, we're going to see an increase in the pressure because we're going to have a lot more collisions. But in the case of Charles' law, we want to keep the pressure constant. So what happens in this situation is, okay, I gotta give everybody a lot more room. So what we will actually see is an adjustment in the volume will actually start to increase to give everybody a lot more room to fly around in because they're moving faster. So now they have more space to move around in. Even though they're flying faster, it will keep the number of collisions relatively constant. And that's what's going to allow it to keep the pressure constant is the volume is going to adjust to allow those collisions to remain constant. Opposite is true as well. If we had a container and we lowered the temperature, we're going to see the pressure start to drop like we did on the right. So once again, the volume adjusts to a much smaller volume, and the volume will go down in this case. Thus, even though they're moving slower, we're basically going to shove everybody together, and that's going to allow those gas molecules to maintain the proper number of collisions to keep the pressure constant. So the way the Charles law works to keep the pressure constant is the volume adjusts to allow the pressure to remain constant around the number of collisions to remain constant. We do not get that effect over here because our volume is rigid, which means the thing can't move up or down. It's got to stay fixed. The way you can move a volume, right, is have like a movable piston, kind of lower it and raise it and give everybody more room and less room in a container. Any question on those relationships? So In each of these relationships, basically as one goes up, the other goes up. And as one goes down, the other goes down is basically the relationships that we see here. Now, speaking of these guys here, when you take a plot, for example, of a bunch of gases, of volume versus temperature, sort of a Charles law plot. And if you extend those lines all the way back to the temperature spot, they all hit the exact same number, which is minus 273.15 degrees Celsius. That number should look familiar. That is the number we use to convert to Kelvin. And that's who recognized the relationship here, which was Kelvin, because if you take that and then convert it to Kelvin, add 273.15, you get 0 Kelvin, which he called absolute zero. So because Kelvin recognizes, the deal is pretty much if it is a gas law, all the temperature always has to be in Kelvin. So that should just be the first. You're dealing with a gas law, has to be in Kelvin. You have to add that 273.15 to do so. This includes problems that sometimes confuse students, which is you're given temperatures in Celsius, you're at Celsius. So sometimes people think, well, I give it Celsius, I want the answer in Celsius, I could just use Celsius. You will get the wrong answer. So even if they give you the numbers in Celsius and they want the answer in Celsius, you need to convert it to Kelvin law and then convert it from Kelvin back to Celsius. So you got to always have Kelvin in the gas law, no matter what the situation is. So speaking of that here, let's look at each of these laws. This is Charles' law here. And once again, this is our constant pressure. These temperatures here need to be in Kelvin. The volume doesn't matter. It could be any unit you want as long as they are the same on both sides. And obviously our Gay-Lussac's law, P1 over T1 equals P2 over T2. This is at constant volume. Once again, here our temperature needs to be in Kelvin. And the pressure here on both sides doesn't matter as well, again, as long as they are the same units. Any questions on either of those there? All right, let's try one here, perhaps. An experiment has 452 milliliters of a gas that's used in a light bulb, goes from 22 to 187 degrees Celsius. What will be the final volume? So take a moment and see what you come up with here. Okay, let's take a look. And once again, I'm just going to pull out the information. I got a volume that is 452. I have a temperature that's 22 degrees Celsius. I have another temperature of 187. And we are looking for a volume in this particular case. Once again, that should eliminate this gas law as we have no pressures. That should also eliminate, obviously, that gas law as there's no pressures. And again, you could kind of see Charles' law there. We're going to call these guys ones, these guys twos. Once again, our temperature always got to get converted. So we'll convert each of these by adding 273.15. That's going to give us here 460.15 Kelvin and 295.15 Kelvin here. Taking our V1, T1 equals V2, T2. We're solving for this guy. So once again, we're going to move the other guy to the opposite location, which means it's going to go to the top. We're basically multiplying both sides by it. And that will give us a V1, T2 divided by T1 is equal to V2. Popping in our numbers in the right spot. Our first volume, 452. Our second temperature in Kelvin. And divided by our first temperature in Kelvin. Kelvin cancel leaves us milliliters as our answer. And that's going to be 452 times 460.15 divided by 295.15, about 705 milliliters. Any questions on that one there? Once again, we can look at what's happening here to make sure it sort of makes sense. Temperature went up, which means our volume should also go up. It went from 452 to 700. So again, it went in the correct direction here. Question on that calculation there. Okay, continuing on then here. Our good friend Avogadro's next. He had a number, but he always wanted a gas law, right? So we do have Avogadro's law here. And when we think about our friend Avogadro, we think about hopefully a mole. So no surprise in here that his gas law actually involves moles. And it's actually had two different relationships, constant temperature and pressure here. And N is actually the number of moles. So this is V1 over N1 equals V2 over N2. It is a gas law like all the other gas laws that you can plug and chug into there and solve for any of those things that are missing. But there's also another relationship that happens as a consequence of Avogadro's law that involves stoichiometry. So we're just going to look at that relationship here for a second. Again, you could just use it as a regular gas law as well. And what we see is as the volume increases, the moles increase the same. So as we have one volume, we have 1 mole, 2 moles, 2 volumes, 3 moles. And what that does in terms of stoichiometry is if you happen to have a stoichiometry problem where everybody's gases and you're at constant temperature and pressure, so that's also really important. You need to be there. You can do a relationship very much like a stoichiometry problem, but involving volumes. So for example, if I had 3 liters of N2 and I want to know how many liters of NH3 would I produce in this case, I could look at this equation, and normally when we would look at it, we could say that there are 2 moles of N2. Give me 2 mole, I'm sorry, no, we don't. We say 1 mole of N2 has 2 moles of NH3. But because of this relationship here, we could actually do it in volume. We could say 1 liter of N2 would give us 2 liters of NH3, almost the exact same way as we do a mole to mole relationship. What that will allow you to do is that, frankly, avoid having to use like a gas law or anything like that to solve this problem. You could just do like a stoichiometry problem involving volumes. So I would do my 3 liters of N2. I would use my relationship of 1 liter of N2 is 2 liters of NH3. The liters will cancel, and that will give me 6 liters of NH3 would be produced in this case. So in a specific situation of temperature and pressure is constant, and you're just kind of looking for a volume to a volume sort of relationship, you could do it just like you do with stoichiometry, a mole to mole relationship. And as we'll see later on this chapter, it can sort of help not have to use a gas law to solve these problems. You actually could just kind of do a volume to volume, mole to mole sort of relationship. Any questions on that there? We will see more of that a little bit later on in this chapter. Now, taking together everybody here, Boyle's, Charles, Gay-Lussac's, Avogadro's, we get the granddaddy of them all, which is the ideal gas law, which is PV equals nRT. A couple of things about this gas law here is it's different than all the ones that we've looked at so far because it's like a one and done situation. There's 1 pressure, 1 temperature. There's not like 2 pressures, 2 volumes or anything like that. It is also the most restrictive in terms of the units. When you use the ideal gas law, pressure has to be in the units of atmospheres. Volume has to be in units of liters. Moles should be moles. And temperature has to be Kelvin. And the reason for all that is R. R is a gas constant, 0.08206. It has units of liters times atmosphere, Kelvin times mole. So that is why everybody else has to be in those units for them to sort of cancel out correctly. A lot of books will round this number nowadays to 0.0821. I personally use the other number because that's what they beat in my head and I can't get it out as much as I try. That is the number I always have. That number is also really important, and clearly you need to know that number as it will not be provided for you. So make sure you know it. But more importantly, in a lot of problems, they will not mention anything about the gas constant. It is one of those values that they just assume you know you have. So if you feel like you're missing something, it's probably the gas constant. And again, in a lot of problems, they really don't mention anything about the gas constant. So again, just like a value you always sort of have available to you. What is an ideal gas? It's a gas that basically, under normal conditions, is how they behave. And there's really two things, as we'll talk about, that make something an ideal gas. One of the things is the volume of the gas molecules itself is actually negligible, very small compared to the container they're flying around in. So when we do problems in ideal situations, we're not really interested about the volume of the gas itself, but we're more interested in the volume of the container the gas is flying around in. That's why we think about it filling it uniformly. So when you read a lot of problems, they'll oftentimes talk about the volume of the container rather than the volume of the gas. The second thing that makes something an ideal gas is you could have multiple gas molecules together in the same container, and pretty much they will behave like they're in there by themselves. So there'll be no interaction between other gas molecules. So even though there's multiple ones in there, they're basically sort of behave like they're in there by themselves. And that's the two things that make something sort of an ideal gas. Now, a couple of other really important things that go with the ideal gas law is, first off, STP. STP is standard temperature and pressure. And when somebody tells you you are doing this at STP, they're actually giving you values. The temperature is 273.15 and the pressure is 1 atmosphere. So when you have it given to you at STP, those are the two values that you should use for temperature and pressure. And if they are at those values, then you're at STP. There's actually a really nice conversion that you could use if you are at STP. So if you're at STP and you do need to be at STP conditions, 1 mole of any gas will equal 22.414 liters. And that's sort of a conversion factor that you could use. So with this conversion factor, just so we're clear, you do have to be at STP conditions. So if the pressure is not 1 atmosphere or the temperature is not 273, you should not use that conversion. You should use the ideal gas law. Where it could come in to advantage is you could kind of use it in certain cases at STP and not have to use the ideal gas law. You could actually just use this conversion factor. The good thing about the ideal gas law is it's universal, which means you could use it under any conditions. So if you want to use it under STP conditions, for pressure, you put 1 atmosphere in, and for temperature, you put 273.15, and you use it. If you want to use it for non-STP conditions, you could use it for any conditions. So if you don't even want to worry about that conversion up on top, don't worry about it. Just always go into the ideal gas law and you'll be fine. It'll come out the same. So, but you could only use that conversion under those conditions. That, by the way, is how we get the gas constant, by rearranging the ideal gas law and solving for R. And under STP conditions, we have 1 atmosphere for pressure, 22.414 for volume, temperature, and moles. And that is basically, again, how we get that 0.08206 number, by putting it in there under STP conditions. So sometimes people see STP and go, I don't have any values. Again, those are the values you should use. And that is basically what they're giving you. Let's take a look at one here. Calculate the pressure exerted by 1.82 moles of a gas at a volume of 5.43 liters and a temperature of 69.5 degrees Celsius. Okay, so let's take a look. Once again, we're going to pull out the information here. We're looking for a pressure. We do have moles given to us, which is 1.82. We do have a volume of 5.43 liters, and we do have a temperature of 69.5 degrees Celsius. So once again, obviously, we only have one of everything, so that eliminates pretty much all these gas laws, except for really our ideal gas law. Remember that pretty much never given to you in a problem, but you always have the value of R given to you in your head, as it is a constant that you should have. So really the only thing we have to worry about here is units. Moles are good, liters are good, Celsius not good, so 273.15 on that, going to give us a 342.65 Kelvin. I will say, very common in these problems, you may oftentimes be given things in grams and need to go to moles. So a reminder that the molar mass from the periodic table is how we do that. Also very common is you're given volume in milliliters and has to go to liters. So once again, 1,000 milliliters is 1 liter. So those in addition are sometimes very common sort of conversions that you have to do in these type of problems. We're actually pretty good on everything else here. So we're going to go PV equals nRT. We're going to solve for pressure. We're going to send volume down below there, and that's going to be P is equal to nRT divided by V. Putting in our numbers here, our N of 1.82 moles, our R 0.08206 liters, atmosphere, Kelvin, and mole. Our temperature 342.65 Kelvin, all divided by 5.43 liters. Liters cancel, Kelvin cancel, moles cancel, leaves us atmospheres left over, which is good because that is a pressure. That's going to give us 1.82 times 0.08206 times 342.65 divided by 5.43, 9.42 atmospheres as our pressure. And again, those other conversions very commonly done, grams to moles and milliliters to liters. Any question on any of those there? All right, so that's the ideal gas law. Feel like we should have another gas law. Good idea, because we still have room on our paper somewhere. Let's talk about changes in all three variables, which is pressure, volume, and temperature. So if we actually take the ideal gas law and solve it for R in two different situations, because R is a constant value, you could then set these guys equal to each other. In most cases, the number of moles will not change unless you open the lid, I suppose. But in most cases, the moles probably won't change all that much. So that gives us what is sometimes referred to as the combined gas law, which is basically P1 V1 over T1 is equal to P2 V2 over T2. Much like all the other gas laws here, we need Kelvin on our temperatures. Pressures can be any unit you want as long as they're the same. Volume can be any unit you want as long as they are the same. Now, if I were to, we'll just talk about this formula here for a second and sort of the importance of this formula, which is if you have to know all these gas laws, which you do, has to know all these gas laws. If you were going to invest your time in knowing a gas law, I would know this gas law, and perhaps I would know it in this version of this gas law. And the reason I say that is, for example, if we take this version of the combined gas law, which is P1 V1 over N1 T1 equals P2 V2 N2 T2. And let's say we come across a problem where there's no mention of temperature, there's no mention of moles, or they're held constant. All you have to do is scratch those out. And there is our friend Boyle's law, basically staring at you. If you take this guy here, and you come across a question where there's no mention of pressure or moles, our pressure and moles are constant. You cross those guys out. And now you got our friend Charles' law right there staring at you. If you take this guy here, and you come across a problem where there's no mention of volume or moles, or they're held constant, you cross those guys out. And now you have Gay-Lussac's law. If you take this guy here, and you have no mention of pressure or temperature, you cross those guys out. And now you have Avogadro's law. So pretty much all those individual laws that we just talked about you pretty much can get from this guy by just crossing out what is held constant, what's not mentioned in the problem, and you could hit all the other gas laws that you need. So if you remember this gas law here, which is what I would probably invest my time into doing, and remember and write it right. The ideal gas law, pretty much you'll have every gas law that you would need to solve any type of problem without having to maybe individually remember all the other gas laws. Any questions on how to do that there? Yeah. So really good gas law in that sense that you can do that. Now, speaking of the combined gas law, this is oftentimes the one that people have a very difficult time sort of rearranging and solving. So if that is a problem for you, make sure you do take some time to figure out how to properly sort of rearrange it. This is usually the one where people always kind of inverse numbers and put the wrong thing on top and the wrong thing on the bottom and stuff like that. Any questions on that there? All right, so I think that's a good place. We'll lay it up there.